This video covers non-conservative forces and power. So as far as energy is concerned, we've only ever talked about conservative forces, like gravity and springs. But now we're going to talk about non-conservative forces. But before that, we need to know the difference between the two. Now, I know it's a lot, but it is important that you write all of this down because it is one of the few times that you'll actually be tested on vocabulary. Now, for a conservative force, the work done by a conservative force on a particle moving between any 2 points is independent of the path taken. So that's the most important part of this piece. And in class, I'll show you a couple of examples of those. Also, the work done by a conservative force on a particle moving through any closed path is 0. The work done by a conservative force on a particle moving is related to a negative change in potential energy. And we'll see examples of all three. For a non-conservative force, work is path dependent, which means that forces such as friction or a drag are going to change the amount of work done depending on the path taken. Okay. Also, the work along a closed path is not 0, so it's basically going against all the three properties that we talked about before. Now, here, work may be related to a change in potential in a total energy, so change in total energy, and that includes thermal energy. So this part you don't need to write down, but I want to prove the third property of a conservative force. So here it says how much work is needed to raise an object 3 meters. Now in our last video, we said that the work done was going to be equal to our change in this case, potential energy. So work is equal to a change in potential energy, which is mgh final minus mgh initial. Now we can assume that our initial position would have been 0, so this piece goes away. So the work needed to raise an object would be equal to mgh. Now, work done by gravity is actually going to be the negative of that. So, the work done by a conservative force is equal to a negative change in potential. Now, the reason that it's negative is because we said work is going to be positive if it speeds an object up, or negative if it slows down an object. Also, force would be positive if the force and the displacement are in the same direction, and negative when they're in opposite directions. So if I'm lifting this object, if I'm applying that upward force and my displacement is upwards, then the work that I do is positive. But if gravity always acts downwards and the displacement is upwards, then as I move this object up, the work done by gravity is negative. So because gravity is a conservative force, then the work done by gravity is negative change in potential. Now, this is also true if we think about springs. Now, this problem says how much work is needed to move a box attached to a spring by 0.5 meters. Now, again, the work that I need to do in order to move the box 0.5 meters is going to be equal to our change in spring potential energy, which is equal to my final spring potential minus my initial spring potential, which in this case happens to be 0. So again, the work that I need to do is equal to 1/2 kx squared. But again, the work done by a spring is equal to my negative change in potential. Again, if I'm applying a force in the same direction of my displacement, then the work that I do is positive. But the work done by the spring, which provides an opposing force, is going to be a negative work done by the spring. So again, this tells us that a spring force is a conservative force. So if the work done by a conservative force is equal to a negative change in potential, well then we can look at one of the other equations we wrote last time, which was work is equal to the integral of f dx. Now, last time I did write f x dx. This is not an error. This is simply saying that the force varies as a function of x. But since that had some confusion, I went ahead and just not included it here. Anyway, all of that is equal to our negative change in potential. So this form of the equation can now be written two ways. This is one way. This is the other way. And basically, they are opposites of each other. So these two bottom equations are really what I'd like you to write down. Now, there's several ways that we can see this in a problem. Now, we can either be given a function of a force that varies with position, which is what that f of x again means. And then we can use that to determine a potential energy of that, or we can also be given a graph. Okay? And remember that a derivative means the slope of the tangent line. So if force is the negative derivative of potential energy with respect to position, then I can look at a position versus, or a potential energy versus position graph, like the one I have over here, and determine what the value of my force is at different points. So let's say I was looking at point E. I would draw a line tangent to that, and then I would say that the derivative at that point would be a positive value, but the force is a negative derivative of that. So at point E, my force is actually negative. Same thing if I go to point C, the negative derivative of that would have been positive force. And then let's say I looked at point B, well then the negative derivative of that would just have been 0. Now, doing work against a conservative force stores energy, which we've seen before, that if we lift an object, we are increasing its potential energy, and when we let it go, that potential energy turns into kinetic energy. So when the conservative force does work on a particle, that energy is released. When a non-conservative force are involved, the energy leaves the system and moves into the environment. Again, energy is still being conserved, but now within our system, that energy is being transferred and turned into something else, usually heat or sound. So this chart is going to help us approach our energy problems from now on. We've seen this before. It said that all of our mechanical energy at the beginning was equal to all of the mechanical energy at the end. But now we're involving non-conservative forces, such as friction. So when that's true, then our mechanical energy at the beginning is not going to be equal strictly to our mechanical energy at the end, but there will be an addition or subtraction of the work done by the environment. Okay? So what that means is that we want to look at what type of energy we have at the beginning, what work is being done on our object, and then how that changes our mechanical energy at the very end. So this chart would be a good idea to write. Now again, friction doesn't have to be the only non-conservative force in this case. We could have also had an applied force that makes our object speed up along the path taken. So we could have used a positive or negative depending the direction of that force. Also, when friction is involved, you need to make sure that you remember that friction has to do with the normal force. A normal force is sometimes mg, sometimes mg cosine theta. So it's important to understand the difference. Okay. Remember that mu is our coefficient of friction, and mg was our force. And r, in this case, is the distance that friction travels over some path. Again, mu down here is our coefficient of friction, and mg cosine theta is our normal force. Now, the next couple examples that we're going to go through, you don't necessarily have to write down because every situation is going to be different. So it's better to just kind of understand where all these pieces are coming from instead of writing every specific situation down. So, this example says a mass initially at rest slides down a rough incline. Determine the speed of the mass after sliding a distance r measured along the incline. Okay, so here we have an incline with some angle theta, and we have this mass that's been placed on it. Now, again, it's initially at rest, so the type of energy we have at the very beginning of our situation is going to be mgh. Now, it says that it slides down a rough surface, so some distance r. And then at the end, we're going to have a speed. So at the end, it's telling us we're going to have some kinetic energy. So again, at the very beginning, we have mgh. So I can say mgh, and then again, friction acts against my object to slow it down, so it's going to be a negative work done by friction. So mu mg cosine theta times r, and then h naught would have been here, and r is the distance traveled down the ramp. And again, the energy we had at the beginning minus the energy removed from the system to the environment by friction, which is this piece right here, is equal to the mechanical energy we have left over, which in this case is kinetic. In this other example, we have a mass of m equals 2 kilograms starts from rest at the top of a smooth, frictionless quarter circle of r is equal to 3m. When it reaches the bottom of the curve, it hits a horizontal section of track that is rough and has a coefficient of friction mu is equal to 0.3. Determine the horizontal distance d that the mass moves through before coming to a rest. So again, at the very beginning, we have only potential energy. So we have mgh, where in this case, h is r. It's going to say 3. It's r. Okay? And then at the bottom, after we've reached this rough patch, we've removed energy and let it out into the environment. So now we have lost mu mg r. Again, because this is a horizontal surface, our normal force is just going to be mg. And then at the very end, we actually don't even have kinetic energy. We have zero mechanical. Or you can say that we have kinetic energy, but that our velocity is going to be equal to 0 at the very end. So then our mechanical energy at the very end would have been 0 either way. So again, the whole point of this is to solve for the distance r, the distance that it traveled along the horizontal surface in order for it to come to a rest. In this example, a 4 kilogram mass starts from rest at the top of a smooth frictionless quarter circle of r is equal to 2m. When it reaches the bottom of the curve, it moves 3m on a rough horizontal section of track, mu is equal to 0.2. When it reaches the end of the track, it launches off a 1.5 meter tall drop. Determine the horizontal distance x that the mass moves through before striking the ground. Again, the same situation like we had before. We are trying to solve for the distance in which it moves through. But now, at this point, I'll call this point 2, we're still going to have some kinetic energy. So, in the previous problem, we didn't have any kinetic energy. That friction slowed us down to 0. In this case, it's only slowing us down to v. So, at the beginning, we have mgh, where h in this case is 2 meters. Again, we're losing energy because of friction along that path of 3 meters. And at the very, very end, at position 2, so this is at position 1, at position 2, we're going to have kinetic energy. Okay. Now, the problem actually asks to determine the horizontal distance x. Well, at this position 3, from position 2 to position 3, it's actually a horizontal projectile problem. So in order for us to figure out how far it goes in the x direction, we actually need to solve for the velocity. So here, we can simply say that 2 times mg h naught minus mu mg r, and actually our m's canceled out here. is equal to the square root of that whole number is equal to velocity. Again, the second half of this problem is simply a horizontally launched projectile. So using information that we've previously learned, y is equal to 1/2 gt squared, and x is equal to v naught x, or vx times t. And then we can solve for x, the distance traveled in the x direction. Now again, we have a very similar problem. We have a 5 kilogram mass that starts at a certain height, which means we're going to have gravitational potential energy. It moves over a rough track. So we have energy lost due to friction. And then we want to know how much it is going to be compressed onto our spring. So we're going to have spring potential energy at the very end. So again, we have mgh. Again, where in this case h naught is 4 meters. We're losing energy due to friction. And we are going to convert all of that energy, including that thermal that we lose to friction, into kinetic energy, to spring potential. And so in this problem here, we're trying to solve for x, how much it is compressed. And our last little topic under this video is power. Now, work is energy, and the rate at which work is done is referred to as power. Now, power is in units of joules per second, okay, because work is in units of joules and time is in units of seconds, so power is joules per second, and this is called a watt. Now, when you talk about average power, you're talking about a change in work over a change in time. When you're talking about instantaneous power, then you want to talk about the derivative of work over the derivative of work with respect to time. Now, remember that work can also be written as the dot product of force and displacement. So if we rewrite the top part as F dot R, we can see this piece right here, dr over dt, which if you replace r with x, which again is just displacement, then this becomes F dot v, because dx over dt is equal to v. So another way to write power is the dot product of force and velocity. Now, this is talking about the dot product, meaning, again, the two things that are involved need to be in parallel with each other. So another way to write this exact same equation would be F v cosine theta.